Hey everyone, this is a video lesson that I'm using in my EP Calculus AV class, and I'm putting online in case it would be helpful to others as well. In the description of this video, there is a link to a printable set of guided notes that you can use to follow along with the examples that I go over. In this section, we are going to discuss an integration technique called integration by substitution, or you will hear me call it U-sub. Okay, in the guided notes, the first thing that you see, the whole front page, is just things you should actually already know, properties and formulas for integrals, indefinite integrals, or antiderivatives, that you're going to need to reference a whole lot as we work through this section. You're going to see that all of the indefinite integrals are written in U form. Okay, for right now, I just want you to look at u as a variable like x, but as you'll see a little bit later on, we will define u as a function whenever we perform what's called u substitution. Okay, so again, this is just like stuff you should know. You have a constant multiple property, a sum and difference property for integrals. The red note here is really important, though, to understand. You do not have a property of integrals that says when you are integrating over a product, you can take the integral or the antiderivative of each part of the product separately. We do not have that. Notice that this says does not equals there. Okay. In the power formulas box, you have your antiderivative power rule and your special case when the power is a -1 power. Remember that is the antiderivative of that is the natural log. And we have our trigonometric formulas, and this exponential formula is the only one you're really going to see in this section. And as you can see, I crossed out the last two here, your logarithmic formulas, because we don't really need those. The only thing about logs that you need to know for this section is that when you have something to the -1 power, the antiderivative is the natural log. Okay, so those are just different formulas that we will reference as we work through our examples today. Okay, so let's start by reviewing the chain rule for differentiation. Okay, we're going to do derivatives first. Take a look at this little review section here. Let me get my pen set up. Oh, maybe it already is. Okay, review. Find the derivative of the following functions. In A, we have the quantity x squared plus 7, all raised to the third power. We're going to do a derivative, which we can denote as y prime, or dy dx. And we're going to use the power rule with the third power first, and then also chain rule. Okay, the 3 is going to come down in front of the parentheses. Keep what is inside the parentheses the same, and take 1 away from the power, so now it's a power of 2. We then multiply by the derivative of the inner function, and the derivative of x squared plus 7 is 2x. Okay, let's put these pieces on the outside together, and let's call our derivative 6x, 3 times 2x is 6x, times the quantity x squared plus 7 squared. Now, before I move on to part B, look at this therefore. See how this is set up for you? Okay, so therefore, what is the integral of 6x times the quantity x squared plus 7 squared? What is the antiderivative? It's up here, right? It's x squared plus 7 cubed plus c. Okay, did you see how that's set up? What I want to draw your attention to is that this 6x part, you see it here, you see it down here. It is only there because the 3 came down, okay, but then also because of chain rule. The x part is there because the derivative of x squared is 2x. And so when you do the antiderivative of something like this, you kind of have to know if part of it is there just because of chain rule. Okay, let me show you another example with part B over here. If my function is sine of x to the 4th, that's a composition of functions, then I'm going to take the derivative with chain rule. The derivative of sine is cosine. Chain rule says bring along that inner function, and then multiply by the derivative of it out here, and the derivative of x to the 4th is 4x cubed. Okay, or I could rewrite that as 4x cubed in front of cosine of x to the 4th. Again, this 4x cubed part is only here because of the chain rule. So if I give you something like this and I say find the antiderivative of it, the only thing you're actually going to focus on is the fact that the antiderivative of cosine is sine and the inner function is x to the fourth. That's our answer here, plus c. That's the function that when we differentiated it, we got 4x to the third times the cosine of x to the fourth, right? So you don't take the antiderivative of 4x cubed. You kind of ignore it when you're doing this antiderivative, the integral of 4x cubed cosine of x to the fourth. Okay, so that's the types of problems that we're going to see where what we're looking at is a derivative that got there from chain rule. And we're going to have to figure out how we can do that backwards. Okay, or come up with the antiderivative. Okay, so normally when I'm in class with my students, I tell them to try these problems and, I just sort of let it go and see where it goes from there. Some students do really well with it. They catch on right away. They can figure out which parts they ignore because they're there from chain rule and, all of the other little bits and pieces that they have to figure out, while others sort of struggle and say, I don't even know where to begin. I don't know where you are, which category you're in, or if you're somewhere in between. So I'll just say if you want to try these and want to figure out the answers before I just tell you, go ahead and pause now and try them. But here they are. Here's the answers. What is the antiderivative? I'm just going to be sure that I have them correct here. What is the antiderivative of 2 sine of 2x dx? Well, it is just negative cosine of 2x plus c, right? Yeah. Okay, the antiderivative of sine is negative cosine. This carries along. I don't do anything with this 2. I don't carry it down into my antiderivative answer because that 2 is there from the derivative of 2x. So it will emerge when we take this derivative with chain rule. Okay, number 2 is a bit trickier. What's the antiderivative of this? Well, the only thing you actually focus on is the fact that you have a second power here and you make that into a third power. But I guess that's not the only thing you focus on because there are some constants as well. Okay, the answer to this one might scare you a little bit if you didn't try it for yourself, but that's okay. We'll figure it out after we learn what's called U sub. Okay, it is 1/12 times 9 plus x to the fourth quantity cubed plus c. That is the antiderivative to number 2. Okay, so if you can't look at these two, try these and figure it out, I have good news for you. We have this thing called integration by substitution, which is a process that you can follow that will help you do chain rule antiderivatives or chain rule backwards. Okay. Now, here are all of the steps that I believe you should take whenever doing integration by substitution. Okay, if you want to pause and write those down now, you can. I'm going to go back and refer to them, as I go over the first couple of examples with you to show you what I mean, though, and we'll do that now. Okay, so let's just jump straight into example 1, where what we're looking at is the integral of 6x squared times the square root of 5 plus 2x cubed. Okay. So here's the first thing that I do, and not a lot of teachers tell you to do this, but I think it's really helpful in understanding where all the pieces are going to fit. Okay, I want you to look for the composition of functions. If you are going to use integration by substitution, you should have a composition somewhere. And I see it right here. I see a square root, but it's not just a square root of a plain x. It's a square root of 5 plus 2x cubed. And I want you to write that part first. Okay, I call this rearranging the integrand. Put the square root of 5 plus 2x cubed first. Put the 6x squared dx in the back. Like that. Now, we call this U substitution because you are going to write a little statement now. It starts with let U equal. And what you are going to do is you are going to let U equal the inner function in the composition. Not the entire composition, but the inner function. That would be the 5 plus 2x cubed. Okay, so this is going to turn into a new integral with just the square root of u in it. Okay. Second part, though, is what does this stuff become? What does 6x squared dx become? Okay, well, to figure that out, you are going to take the derivative of u with respect to x, and I would write it like this. Du dx equals, I take the derivative here, the derivative of 5 is 0, 2x cubed becomes 6x squared. Wow, look at that. Oh my gosh. Okay, now let's move the dx to that 6x squared side like this. And this beautiful thing happens where, uh-oh. Okay, no uh-oh. I don't know what just happened. Never mind. Okay, this beautiful thing happens where this 6x squared dx comes out of that equation, and it tells you it's all going to change to du. Okay, so in the steps that we have listed here, we just did steps 1 through 3. Okay, let's talk about them again. We rearrange the integrand. That means we put the composition first, and we let u equal the inside of the composition. We then took the derivative of that equation that we wrote, and we wrote it as du dx. We then rewrote that du dx equation so that the dx was on the right-hand side with the 6x squared, and that makes it fit into the integral like this. Let me show you. Again, what we're going to now do is write an integral, as I already said, with the square root of u, because we said that if we see 5 plus 2x cubed, we can change that to u. So we're going to write the integral of the square root of u. Now, this other stuff matches this equation, and this equation tells us if you see 6x squared dx, you can change that to du, like that. And so what we're now ready to do is we are ready to take the antiderivative of this new integral in u form. Okay, this is called our u form integral. Keep in mind that you might want to rewrite this as a u to the 1/2 power. A square root is a 1/2, and so what you're really doing is power rule here. Add 1 to this power, that will give us a 3/2 power. Take that reciprocal as what should go out in front. So it will be 2/3 u to the 3/2 power. Let's see. Okay, that's not your final answer. Your final answer needs to go back to x form, and that is our last step in our steps here. So we just did steps 4 and 5. We rewrote the integral in u form. We got a u antiderivative, and now we're ready to change the antiderivative back to x form. Okay, that doesn't mean changing u to x. It means changing u to 5 plus 2x cubed. So our final answer is 2/3 times the quantity, 5 plus 2x cubed, plus c. No, 3/2 power. Oh my gosh. I'm a mess today. There we go. Do you see what I did? I made a very common mistake, and I want to say I did it to point it out to you, but I didn't. I just made a mistake. There was a 3/2 power here, and I forgot to write it over here. But then I caught it. Okay, there it is. There's our final answer. Okay, so let's try those steps again. I actually think that the first couple of steps are the most important, to keep going back and saying, wait, what do I do first? What do I do first? And then eventually the rest of it just sort of follows that that's what you're going to do next. At least that's what I usually see happen. Okay, so remember, the first step is rearrange the integrand. And this is a step that you don't have to do, but I kind of feel like it's helpful so that the composition of functions is first, because then you know where to look for your u equation. Okay, in example 2, the composition of functions is this e function, because it's not just an e to the plane x, it's an e to the x squared plus 2x plus 3. Okay, so I'm going to put that part first in my integrand. And then I'm going to put the 2x plus 2 dx behind it like that. Okay, next I'm going to let u equal the inner part of the composition. So that's the x squared plus 2x plus 3. Take its derivative, du dx, and you're going to find 2x plus 2. Woo! We see that right there. in the original problem, right? Move the dx over. And this equation tells you that 2x plus 2 dx can change to du. So we're ready now to rewrite our integral as a simplified integral. That's what your u-form integral is. It doesn't have all this craziness to it. Instead of having e to the x squared plus 2x plus 3, it's just going to have e to the u. Okay, instead of having 2x plus 2 dx, this little equation down here tells you that that stuff becomes du. And that simplifies all of the stuff for you. I don't know how else to say it. So that you know exactly which part you should be focusing on to take your antiderivative. You're just doing the antiderivative of e, which is itself, plus c. Okay, by the way, this is why we wrote all of these rules on the front of our notes, so that you know, if you need to go back and refer to these little rules, you can. The antiderivative of e to the u is e to the u plus c. Okay, and then final step, change u back to what it is defined to be in terms of x, and in this case, that would be x squared plus 2x plus 3. So I have e to the x squared plus 2x plus 3 plus c as my final answer. Okay, and keep in mind, what we're doing here is we're finding the function that when we take its derivative, we get that stuff that we see in the integral. Okay, we're doing an indefinite integral or an antiderivative of this. So we could take the derivative of our answer and we should get what I circled from chain rule. Okay, the rest of this packet is just a bunch of other examples that do get, I would say, a little bit more difficult as we go. Okay, in example 3, you're going to see something similar. However, when you take the derivative, you're going to see that you need to do a little bit more rearranging. Okay, but let's start with the first thing we need to rearrange is that we should have the x to the 5th plus 7 quantity squared first, because this is a function and then another function on the outside. That's our composition. X to the 4th dx goes in the back. Let's let u equal the inner part of the composition, which is x to the 5th plus 7. Oops, I forgot to write u. And take its derivative, which is 5x to the 4th. Okay, here's what I mean by we're going to have to do a little bit more rearranging. Notice that we only have an x to the 4th dx. So when we move the dx over, we're not quite ready to go into our u form because there's this 5 here that we don't see up here. You need this side of your equation to match perfectly with the stuff that's on the outside of the composition, meaning the extra stuff, okay? So this 5 needs to go over to the du side like this. We could call it 1/5 du is equal to x to the 4th dx. And now these things match, and we're ready to rewrite the integral in u form. This will become the integral of u squared. You don't really need the parentheses. You can just write u squared. And this stuff, x to the 4th dx, becomes 1/5 du. Now, if you want to just write it right there like that, you can. However, this 1/5, it's kind of scary in there, okay? And it's a constant multiple. And luckily, because of this constant multiple rule right here, whenever you have a constant multiple, you are allowed to pull it outside of the integral. And so that's what I like to do with things like the 1/5 that we see in this example. Instead of writing the 1/5 right there, yuck, let's put the 1/5 right here and the du back here. Okay, that just means that the 1/5 carries down, and we do the antiderivative of u squared, which is 1/3 u cubed plus c. Finally, multiply these fractions together. That gives us a 1/15th, and change u back to x to the 5th plus 7 with a 3rd power plus c. there's your final answer to example 4. Okay, so as I said, I hope you're seeing at this point that we're pretty much doing the same thing over and over. We're doing our sets of steps just with slightly different types and levels of difficulty, I guess you could say. Okay, when you rewrite example 4, first of all, I'm going to concede example 4 does not look like an integration by substitution problem, does it? However, what you can do is you can rewrite it with the denominator moved up to the numerator, and you're allowed to do that if you put a -1 power on it, right? I would then also put the numerator x squared plus 1 in parentheses beside the dx. And when you rewrite it like that, you can see here's your composition. You're going to let u equal the inside, and you're going to go from there. Oops, I did the derivative. Oh my gosh, I'm ahead of myself here. du dx is 3x squared plus 3. Okay, so this will become u to the -1. And what's going on here? All right, well, I have 3x squared plus 3 dx, and I need it to become x squared plus 1 dx. So if I divide 3 out of these two terms, I can do that. Or moving it to the other side would be even better. It's a 1/3 du. If we multiply both sides by 1/3, we would get x squared plus 1 dx, matching what we have up here in our integral. So this equation tells us to change x cubed plus 3x to u to the -1. This bottom equation tells us to change x squared plus 1 dx to 1/3, let's put the 1/3 here, du. Okay, that means we're going to have a 1/3 on our answer, and our answer will come from the antiderivative of the ln of u, or the antiderivative of u to the -1, which is the ln of u. Oh my gosh, I'm making so many mistakes. Okay, technically it's ln of the absolute value of u. We will talk about that at some point. Right now, just know that we're going to slap some absolute values on that. Okay, final answer, 1/3 ln of the absolute value of x cubed plus 3x plus c. All right, take a look at the next example. These two do not look at all like they should be integration by substitution, right? You just see the integral of tangent x here, okay? But tangent is the same as sine over cosine, right? Or it is cosine to the -1 times sine. So we can rewrite the integral of tangent x dx as cosine to the -1. Okay, that's just bringing the cosine out of the denominator, times sine of x, and now we see a composition of functions. We're going to let u equal the inside, which is cosine. Take its derivative. The derivative of cosine is negative sine. We don't see a negative in our sine function up here, so we need to move the negative to the du side as we move the dx to the sine side. Now this side of our equation matches the extra pieces that we have up here, and we have a negative du. Okay, so let's rewrite our integral as the integral of u to the -1. Sine of x dx becomes negative du. Negative is just a constant -1 multiple though. So you can put that negative way out there and the du here. Okay, and we're going to do the antiderivative of u to the -1, which is the ln of the absolute value of u. Or bring along that negative, it could be ln of the absolute value of cosine of x plus c. Okay, example 6 is a similar process. It's a cotangent though, so cosine is in the numerator, sine is in the denominator, and you would let u equal sine of 7x and go from there. It's a little bit trickier, and just to save us some time, I am just going to pause the video, put in an answer, and bring it back to you without, much explanation. Okay, here is the answer to example 6. The one thing that I want to mention is after you let u equal sine of 7x, the derivative of sine of 7x actually involves a little bit of chain rule itself. That's where this extra 7 is coming from. It's cosine of 7x times 7, because the derivative of 7x is 7. You don't see that extra 7 up here, so you have to move it to the du side as a 1/7. Final answer is 1/7 times the ln of the absolute value of sine of 7x plus c. All right, there's a couple more trig examples here. I think, again, with example 7, I'm going to pause the video and show you the answer. However, I will tell you that the only thing I think you need to do to rewrite this one, this is your composition, but you may want to rewrite it as sine of x in parentheses and then a fifth power on the outside. You're allowed to do that, and that helps you go from there. Okay, again, I'm going to pause the video, put the answer in, and then I will bring it back and show you. And I'm back, and here is the answer to example 7. I let u equal sine of x. The derivative of sine is cosine, so it fits pretty nicely as a u substitution as the integral of u to the 5th du. The antiderivative of u to the 5th is 1/6 u to the 6th, and then we can change that u back to sine of x. All right, finally, the last couple of examples that we have here are ones where we are working with definite integrals, as you can see with the limits of integration. Okay, we're going to go through the u substitution process, and then after we get our final answer, we will just sub in the upper limit minus the lower limit to evaluate from there. Okay, so for this one, there's a couple of different routes you could take here. You see a composition here. However, secant squared is the derivative of tangent. So this might look a little bit weird at first, but I'm going to let u equal tangent x. Okay, I know that's kind of not what we've been doing, but here's why. Watch this. When I take the derivative, I get secant squared. And the only thing I need to do with that equation is move the dx to the secant squared side. And look at how nicely everything is going to fit. This is going to become the integral of u, and then this stuff will become du. Okay, now there is a thing that a lot of math teachers do that I should probably go over with you, but I'm not going to, where you change your limits of integration to u form as well. Meaning when I rewrite this integral in u form, I can't just carry this 0 and pi over 3 because those are x coordinates, and I'm working with u now. Okay, but I'll tell you, what I do is I just drop the limits of integration until I get my answer back in x form, and then I put them back in. I don't know. It just seems to work well for me. Okay, so here's what I mean. I'm not going to use the 0 and pi over 3, but I'm going to change this integral to the integral of u times du. The integral of u du. Okay, the antiderivative of u is 1/2 u squared. I'm not going to put a plus c on it. I'm just going to change it back to x form now, which is 1/2 tangent x squared. And now I'm going to evaluate from 0 to pi over 3, which remember means subbing in pi over 3, the upper limit of integration, minus subbing in the lower limit of integration, 0. Okay, from here, tangent of pi over 3. Let's see, what is that? That is root 3, right? But it's squared multiplied by a half, so that's 3 halves. Tangent of 0 is 0. So that all becomes 0. And so there's our answer, 3/2. Woo! Done. Remember, if it's a definite integral, you could also check in your calculator the answer fairly easily, I guess. This one's a little bit tricky to type in, but not bad. Okay, so I'm going to recommend that you try that one more time with example 9. Here's another example of a definite integral that you are going to get an antiderivative from with u substitution, and then when you go back to x form, you're going to plug in the upper limit of integration minus plug in the lower limit of integration. I'm going to pause the video, put my work in, and I'll show it to you in a moment. Okay, here's the answer. It looks like a lot, I know, but that's just because it is a lot. All right, so notice that I rewrote the denominator as x squared minus 4 to the -1 power, and that led me to my u equaling x squared minus 4. I did the derivative, I moved everything around to fit back in, and I ended up with an antiderivative of just 1/2 times the ln of the absolute value of u. Now, again, u was x squared minus 4, so that's what I use for my limits of integration. I plug 1 in for x, minus plug in 0 for x, and that gets us a final answer of -0.144 approximately. Okay, everybody, as usual, I hope this was helpful. Bye.